Okay, so in this section, section 3, we're going to be talking about reactants, and we're going to have to come up with deciding which one is the if we put two amounts together, how would we know which one of the amounts, they just gave us some amounts, how would I know which one of the amounts is actually going to limit how much I get of my desired substance? So we're going to determine which reactant is limiting. So we're going to we're not going to teach you a new process, but we're going to show you how you can use that process to determine which one is the limiting reactant. And then once you've identified the limiting reactant, then we kind of just do everything else the normal method. And so we're going to be able to calculate, for instance, like it says here, the amount of moles or mass of the product that we're after. And then we're going to be able to figure out which one will be in excess, which one do I have more than enough of. And then we'll have things like theoretical yield. So what you have been dealing with to this point is theoretical. Now we just have to add the parts with, well, okay, then what actually happens, or actual yield, and then from that percent of yield, what am I? Theoretical would be 100%, real life is usually less than that. Okay, so this is what we have to accomplish. So in a laboratory reaction, it's rarely carried out with exactly the required amounts. Okay, so when you do your lab, you probably will actually measure out what we think should be reacting, but in reality, probably one of those will be my limiting reactant. The other one might be what I'll have too much of. So in many cases, one or more of these reactants is presented in excess. That means there's more than enough to make the other one get totally used up. We had one of the labs where I think we were, or not labs, but one of the problems that we did where we had more than enough. We had an excess amount, I think it was oxygen, not sure what it was anymore. So one reactant limits the product of the reaction, and once one of the reactants is used up, then the reaction stops, even though there's still more of the other reactant. There's nothing for it to react with. So the reaction stops when one of the reactants is used up. And the substance that's completely used up, we're going to call our limiting reactant. It limits how much of the product I can produce. Now, so the limiting reactant is a reactant that limits the amount of the other reactant that can actually combine. It also limits the amount of product that can form in a chemical reaction. I can't get any more once it's all used up. Now, the substance that is not used up, in other words, I still have left over at the end, is going to be my excess reactant. Excess reactant. So the limiting reactant is sometimes referred to as a limiting reagent. When I buy chemicals, they often refer to the chemicals I'm buying not as reactants, but as reagents. And I can have different grades of reagents. I can have laboratory grade. In other words, I'm really trying to do this thing precisely. And they have another grade that the kind I get is called student reagents, student grade. We're not doing labs where everything has to be really precise. And it's maybe not quite as pure, but it doesn't usually. It's not, the purity doesn't really affect the results that we get. Okay, so how do I go about determining my limiting reactant? So let's take this reaction between carbon and oxygen, but where we have enough oxygen to make carbon dioxide. You did one problem, I think it was the last problem on the assignment we graded yesterday. Remember, it was carbon plus oxygen formed carbon monoxide. So if you don't have enough oxygen, you get carbon monoxide. That's the reason why you don't grill inside your house in winter to keep warm, because it uses up the oxygen, and then oxygen becomes my limiting reagent. And in that case, I get carbon monoxide instead of carbon dioxide. So according to this equation right here, 1 mole of carbon reacts with 1 mole of oxygen to form 1 mole of carbon dioxide. So they're all in a 1 to 1 to 1 ratio in this particular equation. Now, if you want to picture what's going on, I have, let's say if I have 5 carbon atoms to begin with, then I need to have 10 oxygen atoms, or no, like, okay, this is one of those where you have a limiting one. So we have plenty oxygen, it looks like. We got 10 oxygen molecules. That's 20. And I only need 5, it says. What? 1 to 1, right? So for every 5 molecule or atoms of carbon, I only need 5 molecules of oxygen. Well, here I have 10. So that means I'm going to have 5 oxygen molecules that have no carbon left to combine with. So I can only form 5 molecules of carbon dioxide. That's the ones with green in the middle and the 2 reds on the outside. That's my carbon dioxide. So in this example right here, carbon is my limiting reagent or reactant. Because if I started out with 5, then I can only have 5 carbon dioxide.
Where did you get the 5 of the carbon?
They say in other words, in this example here, they gave you 5 carbons and 10 oxygens, okay? But we know from the balanced equation that we have underneath there, they should be in a 1 to 1 ratio. For every 1 carbon atom, I need 1 oxygen molecule, right? Yeah, but I have 5 carbon atoms, but I have 10 oxygen molecules. I have 5 more than I need, right? So but because I only had 5 carbons, I'm only going to get 5 carbon dioxide molecules. And the oxygen molecules that didn't have any carbons to combine with, that's my excess. So I have 5 molecules of oxygen in excess. So carbon turned out to be the limiting one. Now if I would switch that and say I have 10 carbon atoms but only 5 oxygen molecules, then only 5 of the carbon atoms would have reacted. I wouldn't have any oxygen left over, but I would still have 5 carbon atoms left over if I had just switched the amounts. Because then oxygen was my limiting reactant in that case. I'd have some extra carbon left over. Okay? So we talked about that. Already talked about that. Okay, so let's do a problem. We have silicon dioxide, which is quartz. Like if you had a quartz crystal, that would be it. Or if you had quartz sand, that's a pretty common sand that I think you find along all our beaches, along our rivers that we have around here. If you find sand, it's probably this kind. Is usually quite unreactive, but it does readily react with hydrogen fluoride. Remember, that was the one that we said we could etch glass with? Well, what's glass made out of? Sand, right? Okay, so that's why it reacts. Okay, so here we have silicon dioxide reacting with hydrogen fluoride. They gave us a balanced equation nicely, so we don't have to focus on that yet. And in the process, the silicon's going to combine with the fluorine, so I'm going to get silicon fluoride, which is actually a gas that gives off, and then it gives off water. So let's say I start out with 6 moles of HF and 4.5 moles of SiO2, silicon dioxide. Which one is the limiting reagent? Which one's the limiting one? Okay, so here's what we were given. We want to know what's the limiting reactant or reagent. Which one do I barely have enough? Well, which one's going to limit how much product is produced? One of them is going to have, I'll have too much of. Okay, but we need to find out which one's which. Okay, so here's the method for doing this. we pick one of the products. It doesn't matter which product you pick, you just pick one of them. And the products are either SiF4 or water. You can pick either one, and that's going to be sort of like, we're going to use that as our unknown. And then we're going to work the problem twice. Once for each reactant to find out how many moles of each is produced by, and the one that produces the least is my limiting reactant, okay? So I just pick one of the products. It doesn't matter which one you pick. So if two of you sitting side by side pick different products, you wouldn't, the moles answers that you come up with would not be the same. But you still would pick the right, correct limiting reactant. You'd be able to identify which one's limiting the whole process. Okay, so let's do that. So let's say we just picked the first one. Let's pick SiF4 since it's listed first there. So I'm going to start out with HF to find out how much SiF4 is produced. Yeah, that is in moles already, nicely. So I'm starting here at moles, and I'm just going across the bridge to the other side, the other moles. I'm just going to use a mole ratio. That's all I need to have. So my mole ratio of SiF4, which is my unknown, I erased that up here. Remember, it's always unknown. This is mole ratio. Just put that up here again. Is always unknown over the known. And my unknown is the one I picked, SiF4. It's going to be on the top, and HF is going to be on the bottom. What's the number that goes in front of SiF4? What's my coefficient?
4.5.
My coefficient of SiF4 is what? 1, right, in the equation. And what is it in front of the known? We're starting out with HF. What's the one in front of HF? 4, right? So I'll have, that's going to be my mole ratio, 1 SiF4 over 4 HF. So 1 times 6 divided by 4, can you do that in your head? 1.5? Okay, so if I started out with HF, then I would end up with 1.5 moles of SiF4. Okay, if I used it all up, that's what I would get. Now let's start with the other reactant. I'm not sure why we did it in this order, why we didn't start out with SiO to begin with, SiO2. But if I start with this one, my unknown is still the same one, right? Because I picked it. SiF4 is going to be on the top, and this time I'm going to have SiO2 on the bottom. What's the coefficient in front of SiF4? Same it was in the previous one, a 1, right? And what is my coefficient in front of the SiO2, which is now my known? Well, it's also 1. So this one's 1 over 1. So on this one, I'm going to get 4.5 moles. So if I had, so just kind of iterate here what we're doing, or review. If I started out with 6 moles of HF, and I used it all up, I would only get 1.5 moles of SiF4. If I started out with 4.4 moles of SiO2 and I was able to use it all up, I would get 4.5. So which one is going to give me less? That's my limiting one. Well, it looks like HF gave me less product, right? Less product. So my limiting reagent is going to be HF. HF is my limiting reactant or limiting reagent. That's the limiting one. One that gives you the least, but I have to do it for both reactants, so the one that gives me the least is my limiting one. Quentin?
For the mole ratio, why is SiF4 the unknown?
Because that's the one we picked. We're trying to figure out how much product. They didn't give us any amount of this one, so that's the one I'm trying to figure out the amount. So that's my unknown. Okay, so here's a sample problem. We have black iron oxide, which is Fe3O4. You've seen this once before in where we were figuring out oxidation states. This is the one where, remember, it gave 3/8. No, not 3/8. 8/3, I guess it is. Remember that positive and negative 8/3, that kind of thing. That's that same chemical. Occurs in nature in a mineral called magnetite. That rock has what property? What's in the name?
Magnet.
Magnet. It's actually magnetic. Okay, find this rock, it'll actually pick up metal, iron, I should say. This substance can also be made in a laboratory in a reaction between red hot iron. So if you heat iron up till it's red hot and you blow steam onto it, you can make black iron oxide. So if you've ever seen some like metal bolts that are black on the outside, that's how they make them. Okay, so here we have 3 Fe plus 4 H2O as steam. That's why it says gas. Forms Fe3O4 plus 4 H2O. It's a balanced equation because it has some coefficients, so we can assume that it is. Okay, now, how we know that? When 36 grams of water or steam is mixed with 67 grams of iron, which is going to be the limiting reagent. Okay, which is going to be the limiting reagent. So I have to figure out how many moles each of one of the products. So I'm going to pick one of the products. Which product do we want to pick? And then what mass in grams of iron oxide will be produced once I've identified what the limiting reagent is. And then what mass of the excess reactant. Then if that's true, then too much of the excess do I have? You know, how much is going to be left over when I am done with this reaction? So we've been given 36 grams of water, 67 grams, that should have a grams after that, but I see it's missing. Should be 67.0 grams of iron. What's our limiting reactant? So let's pick one of them. Since we ultimately need to know how many grams of iron oxide have to be produced anyway, why don't we pick Fe3O4 as our limiting, or as our product that we're testing for. We'll pick that one on this one. And then ultimately at the end we have to find out what's my mass, how many grams of the excess reactant do I have left over at the end? Okay, so here we go. First, convert both of these masses into moles. Okay, so in other words, so we have to end up, if you look at over here on the unknown side, we have to get to right there. We can only compare them if they're in moles. If they're in grams, I can't compare them. So I have to get it into moles of, and we're going to pick it for one of the products. And like I said, we're going to pick Fe3O4 first. So we have 67 grams. So in other words, we have to do 2 steps to get here, right? We have to do the molar mass of my first reactant, and then I have to do the mole ratio for that. So my molar mass for iron, if I look it up on the periodic table, is 55.85. So I'll put that on the bottom so my grams will cancel out. And then I'll have my mole ratio, which is my known iron on the bottom, and then Fe3O4 on the top. And from the balanced equation, there's a 1 in front of the Fe3O4, and there's a 3 in front of the iron. So my mole ratio is 1/3. So if I did it started with iron, and all of it got used up, I'd get 0.4 moles of iron Fe3O4. I would get 0.4. Now let's try the other one. Let's try the steam. What if all the steam gets used up? So it said we had 36 grams of water, and we're going to And then the next thing after mass is molar mass of water, which some of you probably already maybe have that one memorized. The molar mass for water, which happens pretty often, 18.02. And then we'll have the mole ratio of Fe3O4, because that's the one, that's my unknown I'm going for. And then I'll divide it by the moles of H2O from the balanced equation, and it's 4, 1 over 4. So I'll end up with 0.499 moles of that. So which one's going to give me the least? Iron or water? Which one's giving me the least?
Iron.
Iron. Okay? So now that we've identified iron as a limiting reactant, now we work the problem starting with that. In other words, we're basically figuring out which one should I be working with then. It's a lot of work just to get to there, wasn't it? But that's the one I'm going to be working with from now on. So Fe, in that we determine that Fe is the limiting reactant. So then that means the other one, steam, must be my excess reactant. Steam is the one I have too much of. And so now let's find out actually how many grams. Do I need to go all the way back to the beginning to figure out the number of grams? No, we already know iron produces this many moles, right? That's the limiting amount. Let's just start from there. In other words, we're already over here. Why go all the way back to the beginning? Let's just start at moles of my unknown that I got from my limiting reactant, which was 0.4 moles of iron 3 oxide. Then we just have one more step. Molar mass of iron 3, not iron 3. Yeah, this is, let's see, what is this one? It's the one that has an oxidation number of 8/3. So I don't know how you say that one, but it's iron oxide. And then, so we'll take 3 irons plus 4 oxygens, and we get a mass of 231.55 grams. And I find out if that's the limiting reactant, I'm going to end up with 92.6 grams of iron 3 or iron oxide, Fe3O4. Okay, so we've answered the first question. How many grams of iron 3 or Fe3O4 am I going to get? I'm going to get 92.6 grams. Now we have to figure out, then how much too much water do I have? So we need to figure out how many grams of water do I use up, right? How many grams do I need to be able to react with all of the iron? That's what we have to do next. Okay? So we know already that we need 0.4 moles of Fe3O4. Let's figure out then how much water do I need with that. Well, it looks like the water I need 4 times as many moles, right? The Fe3O4 is 1, and there's a 4 in front of There's a 4 in front of H2O, right? So I'll need 4 times as much water as I make of iron 3 oxide. So it's 4 over 1, and I find out, and then I have to change that into grams by multiplying by my 18.02, and I find out I need 28.8 grams of water to make 6 grams, I think it was, of iron. I need only 28.8 grams of water. So how do I find out my excess? How do I find out my excess? How much I need, subtracted from how much they gave me. The rest is excess. So 36 minus 28.8, and I find out I have 7.2 grams of steam I don't need. That makes sense so far, the process? So I first pick a product compute the number of moles from, not product. Pick a product, then I pick the amount of moles of that product I get from each reactant, from the amount that they gave us. And the one that is the least is my limiting one. Then I work the problem from there, always. And everything, you notice I always came off the, in this case, since iron was a limiting reactant, I just always started with iron. Okay, last thing to cover in this is something that I think we've done something similar to this, where you compare the actual yield to the theoretical yield to determine the reaction efficiency. Now, remember I said that usually in a chemical reaction, you don't get all the product that you want. It always falls a little bit short of that. So your theoretical yield is, if I just do the problems like I've been doing, that gives me the theoretical yield. They will either have to give it to me or give me a way of being able to measure how much I really did end up with. So when you do that lab I keep referring to, you will then figure out how much I should have gotten to how much did I really end up with, and that will be my actual yield. So most chemical reactions produce less than the theoretical, and we call that our actual yield. Now, why is it that we might not end up with 100%? Well, one of the reasons why, as I kind of hinted, is if we're using student grade reagents or reactants, maybe there's some impurities in it that may form maybe some side reaction that ends up using up some of my stuff. That I want it all to be this reaction, but some of it might get used on a side reaction that's going on with some of the impurities. Not all the reactant might be converted into products. Like for instance, when you burn gasoline in your car engine, it would be nice if all the gasoline would get totally burned up. But it doesn't. We only use about 40% of it. 60% of it is not converted into the products I want, carbon dioxide and water, remember? So the efficiency of a reaction is expressed as you're comparing the actual yield to the theoretical yield. So this is it's just part divided by a whole. Your percentage of yield is just going to be a ratio, and then ratios are just numbers, and we like to say them as percent, so we need to multiply them by 100 to get our percent. So percent yield is actual divided by theoretical. Actual divided by theoretical. You know how to calculate the theoretical. They have to give you some way of figuring out the actual. They either have to tell you that outright, or they'll have to give you a way of calculating it. So here's a problem. Chlorobenzene is used in the production of many important chemicals, such as aspirin, and dyes and disinfectants. I remember in organic chemistry in college, we made aspirin, which is a pain reliever, right? Kind of the older style pain reliever. Now we use Tylenol and ibuprofen. But one industrial method of preparing chlorobenzene, in other words, what we need to make those things, is by taking regular benzene and reacting it with chlorine. What it actually happens is one of the hydrogens gets bumped out and replaced with chlorine in this kind of reaction. So there's now is that balanced? It looks like it is, isn't it? No? Yeah, it is. 2 chlorines, 6 hydrogens. Yep, I think it's balanced. So there's our balanced reaction. When 36 grams of benzene reacts with an excess amount of chlorine, so we've already identified what's the excess reactant. They told us it's chlorine. And the actual yield is 38.8 grams. What is the percent of yield? What is it that we don't know to figure out the percentage? We don't know the theoretical yield. They didn't tell us that. They told us the actual yield, they just didn't tell us what the, so, but we know how to do that. Okay, so I'm gonna start out with 36.8 grams of chlorobenzene way over on the left, and I'm gonna go figure out what the theoretical yield is in grams. So I'm doing the end-to-end part. So I'll start out with 36.8 grams of benzene. Then I'm going to, next thing is molar mass of benzene. 6 carbons plus 6 hydrogens gives me 78.12 grams. So now I've changed it into moles of benzene. Then I got across the bridge my mole ratio. My unknown is the chlorobenzene that I'm trying to find out. That goes on the top, and there's a coefficient of 1 in front of that. And what they gave us was just regular benzene, and there's a 1 in front of that. So my mole ratio is just 1 over 1. Now I'm in moles of chlorobenzene. Now I have to change that into grams of chlorobenzene. What's the molar mass of chlorobenzene? Well, 6 carbons plus 5 hydrogens plus 1 chlorine gives me what? You're close. They were starting to duck already. So I get 112.56 grams of chlorobenzene. That's my theoretical yield. I should, if all of it got used up, I should end up with 53 grams of chlorobenzene. They said I only made got how much? On a previous slide, what was it? How much did they say? Well, they said we only got 38.8 grams. We should have gotten 53. So if I take 38.8 divided by 53, multiply that times 100, and I hit 73.2% efficient. That means that, let's see, 0.8, to be 26.8 grams or percent of it ends up being wasted. So what chemists do often in working for different chemical companies is trying to figure out, what can I do? How can I alter this chemical reaction to raise it above this amount? Because they're saving their company money by doing that. So that's what their job is. What can I do? Maybe I could, can I get the chemicals from a better source? But if I raise my percentage, will it cover the cost of paying for more expensive chemicals? Or maybe I need to make my reaction environment different so that they'll do a better job of reacting. There's all kinds of things. So chemists are very valuable to a chemical company. They're the ones that help them make the most money. Because obviously, a job of almost any company is what? Make money, right? Make their employer money so they have enough money to pay your salary, right? To justify paying you, to have employing you. Why do we have you working for us? Oh, that's right, because you save us money. Or you make us money, I guess is probably the better way of saying it.